Morning. 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 You there?
Yeah.
I can't find that Paul Bunyan problem anywhere. Where did I come up with that?
It was in geometry in the last section, I think.
Oh, it was in geometry. That's why I couldn't find it. It was?
Yes, it was.
I had a thought that maybe that was the case. I could not find it in the Algebra 2 book. I thought I was going crazy. In the last section? Locus of points? I don't see it there either. In your mind, it's the last section or maybe the last couple sections, last chapter? Okay. Still don't see it. Why would it be in circles anyway? Would it have been after the chapter 11 test? Zig? Oh, there it is. I found it. It's in chapter 11.
Okay, sorry. I got confused between... I think I just forgot about chapter 12.
No, it's fine. Some stories say that Paul Bunyan was 10 times as tall as the average human. Assume that Paul Bunyan's bone structure was proportional to that of ordinary people. Strength of bones is proportional to the area of their cross-section. Strength is proportional to the area of the cross-section. That means that there's a scale factor. So if the area of the cross-section is times 10, then the strength of the bones is times 10, but the weight of the bones doesn't go times 10. And that was the point that we had made. It's because the strength of the bone is proportional to the cross-sectional area. It's not a squared to cubed relationship. That's why King Kong cannot exist. Okay, it's 8:30. Good morning, everybody. So the Paul Bunyan problem has been found. Chapter 11, last section of the geometry book. I kept looking last night. I was up for an hour at night looking for that. Oh, Snapple fact. Here we go. A spider's silk is stronger than steel. I've already read that. I found two new ones that I hadn't seen before. The longest case of hiccups. Anybody know how long?
40 years.
30-something years.
68 years of
So
constant.
about twice mine.
That kind of sucks.
All right, and then koala bears are born smaller than the size of a jelly bean. That was, I still can't even believe that.
Are adult marsupials like that?
I don't know.
So your chat set to everyone can talk to people.
All right. So as you're working on this problem by graphing, we're trying to recall what we did before we came. We realized that if you look at those one variable inequalities, there's no y there. That means you've taken one of the dimensions out of the puzzle and you're just looking at a horizontal cross section. How do I know it's a horizontal cross section and not a vertical cross section?
If you only have x.
That's right, because you're only dealing with x. So because you're only dealing with x, you're just locating points that the cross section intersects on the parabola. All right, so it doesn't speak to up or down. We talked about that. And look at how they want the solution. Look at my mouse. That is one way to express the solution. I like this way.
Yeah.
The algebraic way is x has to be between -3 and 2. Okay, we found -3 and 2 by treating this as an equation, and those would be the roots. All right, then you have to test for solutions. Solutions could be to the left of -3 and to the right of 2, or they could be between. All right, so they're either going to be between or they're going to be outside of. So what we did is they made a table and they tested points by plugging in x's into the inequality and seeing if they're true. So you always start with finding the roots. Now we start with our warm-up. They want you to look at this graphically. Okay, so go ahead and try to graph that. So I'll read this to you. Another way to solve ax squared plus bx plus c is less than 0 is to first graph the related function y equals ax squared plus bx plus c. Then, because the inequality symbol is less than, identify the x values for which the graph lies below the x-axis. You can use a similar procedure to solve quadratic inequalities that involve the less than or equal to, greater than or greater than.
Okay. Hey, can you scroll up?
No. You want to see the solution?
No, scroll up.
Oh, up here?
Yeah.
You have a question about this one?
Okay.
Okay.
Yeah.
All right. Well, I got to get that chat open. Let's see. I knew that. Me too. Sure you did. I knew the koala one. Oh, I must have taken. See, I had a meeting last night and I took it off of host only. Now it goes back to host only. You guys always find that out so quickly.
Great, Nigel.
Okay, I got to get this box out of the way. All right, here we go. I'm going to scroll down now to where.
David, it annoys me because it pops up on my screen every 5 seconds.
What happened?
Notifications annoy him.
Oh, you get notifications? Yeah. All right, so here we go.
He's showing the solution.
Here we go. So 2x squared plus x minus 4 greater than or equal to 0. And we're going to solve by graphing. Okay, so actually, instead of just showing it on the board, just let's look at their solution here. The solution consists of the x values for which the graph of that lies on or above the x-axis. Okay, why do they say that? Because when y has become 0, you are on the x-axis. And when it says greater than or equal to 0, that means you are above or equal to the x-axis. All right, so you're looking for values for x that will make that true. So it really is the same as the last type of problem. So look at what they're saying. Find the graph's x-intercepts. Well, they're doing it using the quadratic formula instead of by factoring, okay? And you're going to need to because look at it, it's irrational. See my mouse? That came out irrational. So look, the first step is the same as the first step up here. You're finding the roots. Okay? Oh, they didn't actually do that, did they? They made a table of values without finding the roots. So I kind of was using the strategy for the next example. I would never do it this way. See up here, example 4? This takes forever. This is trial and error. I'm going to make a table of values is not a good way to do it. I think I kind of like missed that. We already did this here. We found the roots, and then you try a solution that's, oh, actually you can look at the graph. Since it opens up, take a look at that. Yes.
If it's greater than or equal to 0, then how come they're only considering the x-axis?
Because it's still the same thing, is that you only have one, it's still a cross section. At those red, where that's red on the x-axis, those are x values, right? That have y values associated with it on the parabola that are above the x-axis. So watch my mouse. You guys can see my mouse, right? Is my mouse at a
Yeah. Yeah, we can see it.
Is the y value of my mouse, where my mouse is the y value there above or below the x-axis?
Below.
It's below, not a solution. What about any of these? All below, right? All of my y values are below. Okay, what about here? All these y values?
Above.
They're above. And what about on the other side?
Also.
Okay, so what are the
For
x?
instance,
So you want
if the y value
all of these points would be solutions if you plug them in to the inequality. Okay, but the inequality, let's come over here. It's only asking you for what x values is that true. See that? So if they're asking you for what x values is it true that these points are going to satisfy the inequality, then your only answers are the x values only. And that's why you see the red shaded region only. Those are the x values that go with y values. Yes.
I'm supposed to the x values of all the coordinates above it. Oh, they'd be different from what they're asking.
How far left does this parabola go? What is the domain on the negative side? Negative infinity, right? Doesn't it keep going to the left forever?
Yes.
Yeah, so that's why all these values to the left here on the red will all be solutions. When you plug them in, you're going to get y values that are way up here, aren't you? Which are above 0, right? And on the right-hand side, all these values to the right.
Oh, I see. It's basically establishing a field of values.
It's no different than what we did up above, but they're just showing you graphically. There's the parabola, but the red part is the cross section of x value solutions. Okay, now the solution, of course, is an xy combination, but all of these, once they took the y out of the equation, out of the inequality, they're only asking for what x values will make it true. Okay. All right. So all these x values they're inputs that come with outputs that are above 0. Okay. All right, and that's it. How do you do the problem? No problem. You find the roots like we've been doing. All right, and then you can test for points to the left, between, or to the right of those roots. It's this. I wouldn't do anything different than what we did up here.
Testing shows though.
The what?
What do you mean by testing points?
Okay, so once you get these roots, and you see
Yes.
you see their values are 1.19 and negative 1.69. Give me an easy value. Let's say an integer value that's between these.
Negative 1.
How about 0? 0 is always a good one to try. Plug 0 in now here. You guys can follow my mouse. If you plug 0 in here, then you get actually you want to plug it into the inequality. If I plug x is 0 in here, you get negative 4 is greater than or equal to 0, is false. So a value that lies in between your roots is false, is not part of your solution set. Now, pick a value for x that is, say, to the right of 1.19. How about 2?
2.
You plug it in, you get 8 plus 2 is 10, minus 4 is 6, which is greater than. So values to the right of 1.19, and then you'll see it's true when you have values to the left. So negative 1.69, pick a value to the left of this one, the negative, -2. Well, -2 squared is 4. 4 times 2 is 8. 8 minus 2 is 6. 6 minus 4 is 2, which is greater than or equal to 0. So that's true for values to the left of.
Mr.
Right.
Oswald,
Now, graphically, you might ask, well, how do you know that all the values are? Well, look at the graph. You can see the parabola, the y values are just gonna get further and further above the further left you travel.
Mr. Oswald, is there any way to determine the range of the inequality without testing points? Just immediately know it from the solutions?
The vertex and the fact that it opens up. Okay.
And so if it opened down,
Then it's going to have a different, if it opens down, it'll have a maximum point instead of a minimum point.
Yes, but how do you determine the inequality values without actually testing points?
The inequality values. What do you mean by inequality values?
I mean the values of x that satisfy the inequality, the ones that are highlighted in red on the graph.
Well, up above, they just tried x values. They plugged them in, and they saw what the y's were, right?
Well, is that necessary?
No. What I do is I find the roots,
Yes.
right? When you find the roots, you're finding these red points. Okay, so then what you're doing is you're saying that I am looking for either values between these points, or I'm looking for values outside these points, right? And
so we have to.
When I say testing, let's look where my mouse is now. This is inside the parabola where my mouse is. It's also between the 2 points. If I try x is 0, I get a false statement here.
Yes, but Mr. Oswald, once you solved it, well, can't you conclusively determine that it's, for instance, if you have negative 1.69 and 1.19 as the roots, can't you determine that it's less than or equal to negative 1.69 or greater than or equal to 1.19 without testing?
Oh, I don't know. Do you have a method for doing that?
No, I was simply asking because
no.
testing doesn't seem very reliable to me.
Oh, but testing is very reliable. It always works every time. Sketch a parabola. Let's see what this says. This says sketch a parabola that opens up and has these roots as x-intercepts. The graph lies on or above the x-axis, to the left of and including x.
Well, that would be a method.
But that's if it's opening up, right? What if it's opening down?
It would still have, the x values would still be extending in the same direction because y is still expanding infinitely.
If this was opening up, then the parabola would be, I'm going to stop the screen share. If here's the x-axis here and your parabola is doing this, and here are your roots, only these values are above 0, right?
Oh, well, that's true.
Only this would give you solutions if it was opening that way.
Well, then that would still give you an answer. And you wouldn't need to test points. No need to test points. Yes, I guess graphing would be the superior method.
I don't know. I like algebraically you have roots, you can quickly plug in to see what's happening between.
Wouldn't it take less time though if you graphed the parabola as soon as you got the question? You'd be able to
actually plugging in. How do you know graphically that you're opening the correct direction?
Well, if A is negative or
you
positive.
don't. No, because you can subtract everything to the other side, and then A will be negative.
Yeah, if you subtract everything, it would be negative. Exactly. So here's the thing. By testing, once I test and I see that my answer is outside, then I know that it opens up because that's the only way. Because if it didn't open up, then it would be in between. The solutions would be in between.
Shouldn't it satisfy the inequality either way, if it's on one side or the other side?
No, if it's opening down in purple here, but the roots.
Then you'd have less than or equal to. then you'd have less than or equal to 0, and you'd still get the same answer, which is all y values to the left or
No, I'm saying in another case. In another case.
no,
right?
but what you said was if you subtract it to the other side.
Yeah, but you're speaking backwards after knowing that it opens up. I'm saying before you knew that, you don't know if greater than or less than negatives, you don't know if that's referring to one that's opening up or down until you know which coordinates are going to be solutions. So,
Mr. Rosenthal, assuming you subtracted it, well, the inequality would change, wouldn't it? It would be negative x squared minus x plus minus x.
Just make these all opposites.
Yeah, plus 4
and less
is
than or equal
less
to
than
0.
less than or equal to 0.
It
but
still
those
doesn't,
two.
It doesn't.
Yeah, but
just opening up or down though.
Yeah, but instead of but the solutions would still be the same. But if you graphed that new inequality, you'd get the same answer because the y values would still be to the left or right of the roots, which means
you're
it's
right.
the same thing.
So you see what Søren's saying is that if I graphed this parabola equal or less than or equal to y, and I got this upside down one, now I want all the values that are less than the x-axis or equal to, which would still be all of those no matter what.
Exactly. So graphing would still work in that case.
Graphing would still work in that case. Yes, you're right. But graphing, think about how long graphing takes compared to if I just try a point, if I just try an x coordinate between my roots, I'll know right away if it's outside or inside. And it's really easy to try 0. If you always use 0 as your first one you're going to try, either 0 is outside or inside your parabola in any given problem, right?
Well, sometimes 0, 0 is on the parabola, which is harder, but then you can just do 1,
Right,
1.
so then you wouldn't, if that's a root, if 0, 0 is a root, then you wouldn't try 0, 0. But in a lot of cases, if you just try x is 0, you can see where the solutions are, and then you can make sense of it that way. Okay. Let's go back. Okay, try this one. Does that one open up or down?
No, it opens.
It opens up.
You're saying it opens up because it actually, you don't know is the answer. We just showed in that last example that it could open up or down and you're going to get the same solution because it's a cross section. How do you know if it opens up or down?
You can't. The greater than or less than symbol, that doesn't affect whether it opens up or down. So Søren's thing, if you subtract them on both sides, the symbol's the opposite. It doesn't matter. It just gives you a different solution.
That's what I said.
Yeah, but you don't know then if that parabola actually opens up or down. And you don't need to know. When they graphed that one up above, it didn't matter if they graphed it up or down. You just graph it whichever way you have the equation set. I presume it's easier for most people to graph it when it's all positive. Okay, less than or equal to 0. Whenever you solve this so that everything's on one side and 0 on the other, you're always going to be using the x-axis. So the roots are always going to be, giving you your solution points, your points of interest for your solutions. They want you to, I don't need you to use a table in graphing. I just need you to solve it your way. I'm going to solve it my way in a second after you guys get a little moment here to do it. I forgot to post the lessons yesterday, but I'm still looking and I'm not seeing many hits. Not a lot of views, like 1 or 2 views, some 0 views. But again, I'm preaching to the choir because all of you are watching it now. It's the people that aren't here, you know, a good 40 plus students that aren't here and they're not watching it. I guess they figure, well, geometry's done, I'll get it next year. But they don't understand. I'm going to be telling the teacher next year that you guys covered this stuff.
Well, Mr. Rosenthal, I don't see any point in trying to get them back now because those same 40 students that haven't been attending the lessons today and yesterday and the day before, they haven't been attending for the entire time we've been doing these Zoom lessons.
I also think that it's possible that some of these students, they're going to another school and they're going to have to do this stuff anyway, and they figure, why do I need to do it twice? It's really the students that are coming back to us that the teacher here is going to know that you guys did this and you guys are going to be ahead. So I don't know.
Do you know what math?
I control everything and I don't want to. All right, here we go. I'm going to do the way that I would do the problem is I would use the quadratic formula if I could not factor it. It does not look like that this can be factored. So I
use completing the square.
Well, that is the quadratic formula. That's the same as you using the derivative when you already have negative b over 2a. We already have what completing the square gives you. Completing the square gives you the quadratic equation, the quadratic formula. So x is equal to, oh, my markers, poor markers. It just has to last another couple weeks. X equals, and I don't know if it is, negative b plus or minus b squared minus 4ac all over 2a. X equals, and I'm using equals. I know that I'm treating it as it's equals to find where the roots would be if it's equality. Oh. Okay, and then what I'm going to get is here I have 8, I have 24, plus, so 28. So that will be 2 rad 7. And then that will simplify into negative 1 plus or minus rad 7 over 2. Then what I want to do is I want to see what each of those are. So I get my trusty calculator out. And I'm going to do rad 7. And I'm going to do minus 1 divided by 2. No. Rad 7, let me do that again. Minus 1 divided by 2. So I have one solution. Okay, and my other solution is rad 7 being taken away from negative 1. Make it negative plus, minus 1 divided by 2. Negative 1.823. Okay, so there's my positive root, there's my negative root. All right, that's where the parabola crosses the x-axis. But one-dimensionally, where are my x solutions going to be? All I'm going to do is I'm going to test a point that's in between those. Since one is negative and one is positive, I'm going to test 0. Look at this. 0, 0, negative 3 is less than or equal to 0. So it's in between these solutions. So I'm going to say that x is between, and there's an equal sign, so you put that, it's between negative 1.823 and I like the using 0 as a test. Okay, and that worked. Yeah. Yes. Say hi to everybody. Say hi to everybody.
Hi. Hi.
Hello.
Oh. Hi.
Oh, where's
Hello.
Oh, I'll get it for you. Hold on, Liz. They can't see you. If you can't see your face, they can't see your face. There you go.
Hi.
You're welcome, babe. You're welcome. Okay, now, so let me review what I did. I treated it like an equals, like an equation instead of an inequality. I used the quadratic formula to find the roots. I then tested a point in between, and 0 is what I like to try because 0 gets rid of everything and it makes it real simple. I look for whether this is true or false. If it's true, then a point in between, all the points in between are solutions. If it's not true, then all the points outside are the solutions. Okay? And that's it. Done.
I used graphing, Mr. Ostal, and given that it was less than or equal to 0, I just drew downwards to see which points fell into the solution
Right.
group, and
That's
it's
fine.
all the points between the two. Yes. Well, actually, not all the points between the two. Some of them went above the x-axis.
Well,
Wait, so
let's look at this real quickly. If I use graphing, and I knew that if I just want to sketch a graph, right? There's my y-axis, there's my x-axis. And I'm sure you found the roots, right?
Yes.
So you label your, okay, here's 1, so here's, 0.823, and then here's 1, and here's negative 1 point.
I don't know. I'm sorry. All the solutions did.
So those are those roots right there, okay? Then what you do is you say, okay, I'm going to treat this right now. I have it on solved this way, so it's less than, right? And this is positive. So I'm going to graph this, and I'm not going to be accurate where my y-intercept is, but I'm just going to graph it like that. I don't know where that is. Now I'm going to say I want everything less than the x-axis. Well, everything under my hand is the loop part. That means everything here is just all the x values that give me all the points on this parabola would give me the solution there, which is what I have there. So that works too, just a sketch. But I thought it was faster, instead of sketching that all out, try a point in between, like 0. 0, x is 0, is what I tried. And I got -3 is less than or equal to 0. Oh, by the way, that means that that's at -3. Okay?
When you were doing the quadratic equation, how did you get root 7 as the part in the square root?
Okay, so x equals -b plus or minus square root of b squared minus 4ac over 2a. Okay. Okay, so 4 plus 24 is 28. Okay, that's 4 times 7. Right? And the square root of 4 is 2.
Okay, yeah. Thank you.
You betcha.
Mr. Rosenthal, do you know what math teacher we're going to have next year?
I do. To a high level of certainty, but nothing certain, but to a high level of certainty, a comfortable level of certainty, I do know. His name is going to be Mr. Nuno.
Yay. Wait, Mr. Rosenthal, I don't understand how you find the range. How do you know which points are the correct solution?
Okay, so once I had roots, see, look at this step. Either my solution is, all of my solutions are going to be x coordinates that are between these points, or they're going to be outside those points.
Okay.
One or the other. So what you do is you just test an x coordinate that is between them, like 0 is between a positive and a negative. Something easy to work with. Plug 0 in and see if it's true. Well, if this is 0 and that's 0, -3 is less than or equal to 0. Yes, true. That means that all points that are between these numbers. Now, graphically, we showed what does that look like. You had these two. Here you had 0.8, and here you had -1.8, right?
Mm-hmm.
The way we have this is the parabola opens up. And you want all the points on the parabola that are going to be less than a y value of 0, less than the x-axis. Well, these points on the parabola are all greater than 0. These points are all greater than 0. And they go on forever to the right, and these go on forever to the left.
Can a negative distribute into a radical?
If this was greater than or equal to 0, you would shade outside. Because all of these points go right and left forever, right? But it didn't. It said less than. So that's only these limited finite points here. Well, actually, there's an infinite. It's just bounded by these 2 points. So all of these are all x, y values on the parabola. Where are all the x values that go with these? They're all between these points. Okay.
But then what about all of the points above and below the x-axis?
Well, all the points below the x-axis are the ones we want. Those points are the solutions to this. But this is saying for what, notice there's no y to be solved for here. It's asking you what x values satisfy.
Oh, okay.
So the answer can only be x values. So where are all the x value only? Well, then it's one-dimensional, so you only get one number line to do that. And that's going to be the x number line. All of these along the x number line are the x values that correspond to all of these other points on the parabola that are under the x-axis.
So if -3 is less than or equal to 0 wasn't true, then would it be all the points outside the parabola?
If this was greater than, right, then you want all the points that are greater than the x-axis, right?
Uh-huh.
So, and what x values do these points correspond to? All of these. And over here, these, as it goes up forever, it keeps going to the right. These are all the x values over there. That's if that's greater than.
Oh, okay.
Okay. All right. All right. All right, here we go. The number T of teams that have participated in a robot building competition for high school students can be modeled by, or middle school students for us, okay? It can be modeled by this. So that's the number T of teams that have participated. All right, and then it'll say where X is the number of years since 1992, for what years was the number of teams greater than 100? See if you can put that together. T of X is your y-axis, X is your x-axis. X represents number of years since 1992. That's only important at the end when you want to interpret what your x values are. Okay. Once you solve for x, then you can go back and say, oh, x is that many years after 1992. You don't need to use 1992 in your calculations. Okay. Number of teams is your y, right? So if you're looking for for what years was the number of teams greater than 100, you are going to write a new quadratic inequality using that equation. You're going to turn that into an inequality with the number 100. Is what you should be doing.
So it would be the quadratic is greater than, or is greater than 100.
Yeah, you see that part to the right of T of X?
Yeah.
But to the left of the comma.
Yeah, just make that greater than.
That's the rule that this situation follows. However, you want to use that rule and you want it to be greater. Let's see, what does it say? It wants to know when the number, for what years was the number of teams greater than, not greater than or equal to. So it should say that that function on the right of T of X, of the equal sign, should be greater than 100. And then you can go ahead and solve it the way we've been doing it. And then you will be applying what we just learned to a real situation. Try to, as you're doing this, don't just do the problem to get the answer. Try to make the connection to what type of problem this allows you to solve. Don't get caught up in the specific problem. Don't think, oh, this only applies to this particular problem, so it's not important. It's not that. It's a tool for maybe you're in the future trying to solve a certain problem and you realize you can use this type of reasoning to do. It's the type of reasoning always, right? The geometry was always about the reasoning, not about the actual problem itself. Life is full of problems. You'll never be done with problems. Okay, I'm going to write the function down. And this is what I got. Hopefully you guys were able to write that down. The function tells you whenever you plug an X in a certain amount of years after 1992, you plug it in and what you get out is the amount of teams participating, right? By the way, it's always expanding, isn't it? And how many teams did we start with in 1992? You could see it in front of you. 35. That number is the amount of teams you started with. This models the growth. Apply this to our gravity problem. Your growth is actually going up. Now, I wonder what this is. This must be students who drop out. Your students leave. Maybe they graduate the program at a certain rate. I don't know. You can try to think what would cause. Remember, this is one-dimensional. This is like an initial velocity, or it's two-dimensional if you want to think of it that way.
Maybe they just had to develop pass through all of the points indicating the number of students.
Say that again.
No, nothing. It's fine.
Okay. All right. So the book solves it by graphing it on a graphing calculator and then just going to, but we don't have to do that. We can do it our way. All right. So here we go. I have 7.51 x squared minus 16.4x. Subtract the 100. Okay. And you get negative 65. Okay, is greater than 0. I have a parabola that is opening up. If you want to do a graphical, okay. It's not on center, so it looks like there's going to be 2 roots here. All right, and we want to know, it looks like, if you look at the graph, you want values that are greater than the x-axis. So it looks like our answers are going to be shaded like that. Look at that. Before we've even done any math, really, graphically, I can already see my solutions are going to be outside my roots, whatever my roots are. See, I did the problem in a different order.
How would you know that?
Because all of my values have to be, if I solve it so that this is all on the left-hand side, my A is positive, so I can sketch it up. And when it's positive and sketched upward, opening up, then it has to be greater, only values above the x-axis. So only these values. And these values correspond to x values that are outside the roots. All of these values that are above zero, all of these values correspond to x values that are outside the roots.
Why not like inside the parabola?
Because all of the values, all of these x values here, they correspond to y values that are below the x-axis. Violates what this inequality says. The inequality says you need points that are above the x-axis. Those are these points. And where are all the x coordinates for these points? Here, forever. So before I've done anything, I already know that wherever my roots are, my solutions are going to be outside of them. Now, let's talk about practicality. Would any of these actually be solutions? If this happens to be a negative root here, what would negative mean? It would mean years before 1992. But we don't care about those. So probably we're looking at those values.
So if they only ask you for after a certain period, you'd only consider one section of the inequality?
In this problem, this doesn't make any sense. They're not asking us for what happened before 1992.
Yeah, but because it's a function and it's a mathematical space, it doesn't care, and that's why we only need to consider the one that comes after 1992.
Yes. Okay, now, let's see. There were more. Is there an upward boundary for this? Did they say anything in the problem that says that we can't go past a certain amount of years?
Yes, x can't be greater than 9.
Oh, yes, there you go. You cannot exceed 9 years. Okay, past 1992. So you cannot go past 2001. So really, we're looking for x values that are between, oh, it even said it in the beginning. It said x has to be between 0 and 9.
It said 0, yeah.
Yeah, so we cannot go past 9 years. All right? Okay, so now we just need to know where that starts. Did it start at year 0? Obviously not. At year 0, we had 35 participants. So somewhere between 0 and 9 years, we went over the 100. Okay?
Right.
So then
0 is greater than or equal to 0, which is greater than or equal to 9.
Sorry, that's x. Okay, so now let's get to it. Let's find out where these roots are. Okay, negative b. So that'll be positive 16.4 plus or minus square root negative 16.4 squared minus 4 times 7.51 times negative 65 all over 2 times 7.51, and I'm going to do the calculator work. And I think if this is bigger than 16.4, which it's going to be, I'm not going to subtract. I'm just going to do the adding because I only want the root on the right. Okay, so here we go. 16.4 squared is 268.96.
Yes.
Okay, and then let's see, that's 260 is 4 times that. So I'm just going to do plus parentheses 260 times 7.51. So this is what I got for the discriminant, what's under the square root. Now I'm going to hit the square root button. Okay? I'm not going to subtract that from 16. I'm not interested in the negative value. I'm going to add to 16. 16.4. Okay, I have that. And now I have to divide by this. So what is that? 15.02. So divide by 15.02. And I get this. 4.2299. So I'm going to say about 4.2. Okay, so for x values, and I now know that it's greater than 4.2, then I'm going to get my answer. All right, and I cannot have values more than 9.
It's greater than 4.23.
Well, we're just going to round to the nearest tenth. Okay, so what does this mean? 4.2 years after 1992, all the way up to 9 years. So between which years is that? What is 4.2 years after 1992?
Like around like 1996.
1996 and 0.2.
Well, at the 4-year mark, that was that season. They had not accomplished it in the 4th year, right? This is more of a discrete situation. They weren't gaining in participants during that season, I would guess. So it was somewhere I would say it was in the 1997 year that they had that many teams. If you have to be discrete, and you have to say, well, in 1996, they didn't quite make it. But by 1997, they definitely had more than enough.
Mr. Ostap, but wasn't 1996 a solution? It wasn't the year for the value for 1996 a solution to the original to the original quadratic?
1996? No, because
Yes.
it didn't happen right upon entering 1996.
Wait, so what was the solution to the quadratic?
What?
Oh, the solution?
4.23.
It was 4.2.
Oh, so you rounded up because 4 wouldn't exactly match.
If I have to give an answer of between what years, let's look at the question.
Then.
What did the question say? Okay, for what years was the number of teams greater than 100? Well, in 1996, it almost was greater than 100. All right? We are assuming some things here. We're assuming they're not gaining participants the whole time. It's not continuous. The graph doesn't know that. The math doesn't know that it's not continuous. This is not a discrete function that we're working with. This is a continuous function. There's no break in the parabola. Okay, but in this practical problem, this is a discrete situation where in 1996, let's say at the very beginning, you had your team set, you just missed the 100 participant mark, right? And then you jumped to the 1997 year, right?
You could forward, I guess.
So you're only jumping by whole numbers. 1 year after 1992, 2 years, right? That's a discrete situation where there's no such thing as 1.5 years and having a different amount of participants. It's 1 year, 2 year, 3 year after, okay? All right. I think we should move on because we've eaten up almost all of our class time. But there's the solution. It's 1997 to 2001, all right? And that was our application of the math. All right. Go ahead and do this one. Solve that one algebraically. Which I think is what we've been doing. We've been using the algebraic method the whole time. So this is just a review of what we've been doing. This one's factorable.
That's factorable.
Yeah. I'm going to cut to my screen.
It's also yeah, I know, but
okay, so this one,
it's fairly easy to do with quadratic formula.
-2.
Yeah, but
the quadratic formula is fine. Okay, but this is going to be 3 times -5. So x plus 3, x minus 5, and I'm going to use the equals, right, just for now. So my roots would be -3 and +5. I want to test a value between. I come all the way back up to the top. 0 is in between. There we go. -15 greater than 0, false. So it has to be points that are to the left and to the right. Now, if I want to graph my solution, here's -3, here's +5. Since that's greater than, can't be equal to, that means you cannot land right on these points. Okay? And I tried 0, okay? And it didn't work. So that means it's all points outside. Okay? Algebraically, I would say that x is between, not including, it's not in between, excuse me. X is less than -3 and, or is it or? I think it's or. You can't have both at the same time. X
Yeah,
is,
it's an and or inequality.
yeah. X is greater than 5. That's it. That's my algebraic solution. That's my graphical solution.
Oh, right, these ones.
Okay. All right, and then let's take a look at the book solution. Oh. Yeah. I was looking at this, see my mouse? I saw the equals and I'm thinking, what's going on here? That was just temporarily. Look, here's their solution. X is less than -3 or X is greater than 5. Okay. It's interesting to me. Why are they testing all of these? It seems to me you just test one that's in the middle. It either is or it is not a solution.
That would take longer, testing all of those, than just testing one.
Yeah, but to me, this suggests that it's possible that there's some other way that it could be. To me, I'm thinking it's not. It's either in between or outside of.
It
says
could just
test
be
the next value in each
less
interval.
than 5
Maybe
and less than
maybe-
-3.
I think for parabolas, it can't be any other way. But if you have functions that cross the x-axis more than twice, right? So let me stop.
Sine functions.
Actually, I realize you don't even need to graph. All you have to do is check whether, just in the beginning, it's going to be the same if you subtract anyway. So just check if A is positive or negative. If it's positive, then it's less than or greater than, and if it's negative, it's between the two.
What if I have this, that some function?
Actually, not negative. If it's oh wait, well, oh no, if it's saying greater than 0, then yeah. But if it's
If
less
the function
than
has to be less than 0, what are the x values that satisfy it here? These, not these. So let me use a different color. All these x coordinates correspond to points on the graph that are, all of these points are below 0. These points are all above 0. These points are all below 0. So this is part of your solution, and these are open circles, because these points are equal to 0, right? So you can't have equal to 0. All of these points are below 0. These are above, and then you would have open shade. So I think that they're telling you to test more than one point, because in the future, in Algebra 2, you're going to be doing the same thing with this type of inequality, where your solutions, you can have different zones that work.
True, but that's true, but for now, I don't think they're going to ask us to do a sine of x inequality or x sine of x inequality.
Well, there's an infinite amount of solutions if it's sine, because it goes on forever.
Yeah.
Or you can just do it in a period, in a certain period, right? And if it's in a period is 2 pi radians, right? So then half of the values in a sine curve, from 0 to pi, those x values are going to be above 0, and from pi to 2 pi, they're going to be below. Right at pi, it's equal to 0. Okay, but you're going to get into that too. All right. Wow, we used up the whole time to finish this lesson. All right, that's okay. 200. We don't need to do 250 participants. I think we're good. All right, guys. So 4.9. I'm going to end it here. And I'm going to give you the homework officially for this. So HW.
Do Friday?
Let's see how many problems there are. Come on, load it, load it. Oh yeah, okay, so there's enough where we're gonna do every 4th problem. Okay, so you're welcome.
Okay.
All right.
So let me just put that up.
Would you like it if we did every even problem?
And I would be proud of you.
If you need it, son, you don't need it.
Oh no, but I started doing every 4th problem for the last. Oh wait, if you.
Yeah, but you know what?
Okay.
I want you to take responsibility of your learning, and I want you to judge whether you need more practice or not. You guys don't
But
need
that's
to
really
be on this
hard.
old system where I'm only going to do it if there's credit and if the teacher wants me to. You're going about this whole education life thing all wrong.
No, it's just that, Mr. Rosenthal, if I say I don't, if I say I don't, I have enough practice and I don't need to do it, well, how can I be sure? I might perform badly the next time and then I might realize that I made a mistake. But if I say I don't have enough, how do I know if I'm wasting time or not?
You don't.
Just if you think you
Nobody's gonna give
understand
you
it,
guarantees.
then you don't need to do it.
By
You
me,
don't need to do every even.
I don't know that either, Søren. So by me being an authority, quote unquote, authority figure doesn't make me correct on that either. By just assigning it generally to everybody, that doesn't mean just because a teacher assigns it that they know that that's going to make the difference for you or not. You're never going to get that kind of guarantee. You use your best judgment. Rely on yourself. You'll be fine. And not
Mr.
always,
Rosenthal.
sometimes you won't be, you know, so that's okay. You learn.
Mr. Rosenthal.
Okay, so that's due Friday. You are dismissed. I'll take questions now.
Thank you, Mr. Rosenthal.
You're welcome.
Mr. Rosenthal, look at it. Wait. Mr. Rosenthal, can I share my screen? Look.
Let me change it to share screen. Okay, go ahead. Yeah, what's that? Oh, tangent of sine of cosine of secant of cotangent of x. Yes, it sounds like you're having fun.
Do the arctangent of that, David.
The arctan of that?
Oh. I think Deathmatch does do arctangent. It doesn't put
So
its foot
what
down
does
and
sine-
say
What
inverse
does
tangent.
sine of a value mean? The sine of an angle is a ratio.
Of
And
the
then you're
opposite
taking
to the
that
adjacent.
ratio and you're treating that ratio as an angle. Right? Because you're then going to take the tangent of that, or the cosine of that, or the cosecant of that. You're treating a ratio as if it's an angle when you're doing that. Sine of cosine, because we define sine of an angle as a ratio. Sine of a ratio doesn't mean anything. Inverse sine or arc sine of a ratio means something.
Wait, if sine is a ratio, well, ratio could be expressed as a rational number.
So you might put arc sine of cosine of x, right? Because cosine of x is a ratio. Arc sine of a ratio is an angle.
Well, could you put? Well, yeah, it wouldn't mean anything. It would just be spitting out values, but you could still do, for instance,
Well, you saw
arc
that it
sine
came out. You saw it came out with a graph. But I don't know what kind of application that would ever have.
None. It's fun.
Well, you never know.
Yeah.
They haven't discovered nearly all the things there are to discover. So who knows what messing around with stuff can yield.
By the way, son, figure out whatever's wrong with your phone because I can't call you. It doesn't work.
You need a face.
Oh no! It's. I got your call. It said missed call an hour ago. The problem was I never heard you. I never heard the call.
Oh. When I did it, it beeped in my face, so.
Wait,
Good. Beep,
yeah,
beep.
this meeting. I think we have this
Yeah, we
meeting.
do. Okay.
You gotta go.
Okay, thank you, Mr. Rosenthal.
You betcha.
Have a good day. We'll see you tomorrow.
No. You have a good day.
Thank you.
Anybody have any questions for me? Jeremiah.
No, thank you, Mr. Rosenthal. Have a good day. See you tomorrow.
Okay. Jeremiah, are you there? Did you have some questions you wanted me to go over? What happens to people who are incoming into the school? I don't know. They come into school. Jared, if you're still there, are you still there? No. There's questions I never got to. Anybody else have any questions for me? All right, I'm going to sign off. I'll see you guys tomorrow. Bye.